Hello, here we are going to discuss data structures and algorithms. Before we start our discussion on that, let's first see what we are going to cover. First, we will demonstrate the need of data structures and algorithms, and then we will discuss how they impact efficiency, and after that we'll reference to some fundamental resources for data structures and algorithms. So these are the things which we are going to cover gradually. So let's start from the beginning by demonstrating the need of data structures and algorithms. So what are data structures? Data structures are methods of organizing and storing data in a way that allows for efficient access and modification. Let's look at a simple example to understand how they work in practice. Imagine we have a list of student scores stored in an array called scores. Now to find the score of the second student, we use array indexing. The index of the second student is 1, which is 90. This allows for fast and direct access to specific elements in the list. And to update the third score, 78, with 80, we simply assign the new value 80 to the index of the third student, which is 2. And like this way we can update the array. This makes modifying data quick and straightforward. So arrays are great example of how data structures allow for efficient access, like how we accessed second score data 90 from the array list, and quick updates like how we updated the third score data to 80, which was 78 before. So arrays are great example of how data structures allow for efficient access and quick updates, making them well suited for tasks like managing a list of scores. But when it comes to inserting or removing any score data, then a linked list data structure will be better suitable here. Let's break it down by comparing how inserting works in an array versus a linked list using the same example. Now we will insert 88 between 90 and 78, means at the third position inside of the array. So we have our array scores. Now let's say we want to insert the score 88 between 90 and 78. That means at index 2, 0, 1, 2, the third position in the array. Here's what needs to happen in the array. First we find the index, that's 2, 0, 1, 2. Then we shift every element after index 1, 0, 1. After index 1 we shift every element. So here after index 1, 0, 1, we shift every element after index 1 position to the right to make a space. Now we insert 88 at index 2. So it works, but shifting takes time, especially with large data sets. Now let's see it with a linked list. Here's how our scores would look as a linked list. Here assume each value is a node linked to the next. Like here we can see each one is a node here, where each node consists of a data value and a pointer along with it, where each pointer references the memory address of the next node in the sequence, which makes it a data structure consisting of a linear collection of data elements. So each value here is a node containing a data value and a pointer to the next node. This structure allows for flexible memory allocation. We don't need to shift anything physically here, just need to update pointers. Now to insert 88 between 90 and 78, create a new node with the value 88, traverse to the node with the value 90, point 90 to 88, then point 88 to 78. The visualization will look something like this. Here we can see a new node with the value 25 is created, then it traversed to the node with the value 20, then it pointed 20 to 25, then finally it pointed 25 to 30, effectively making it a linear collection of data elements, which we define as a linked list data structure. So we are done with the insertion, just the pointer changes needed to be done here. No shifting like array is needed, which is comparatively a time consuming task, and the same pointing and linking process we apply while removing any scores data using linked list data structure. So we can see how the linked list here is more suitable while inserting and removing the data from the linked list. So from our discussion, we know we use array for fast access and linked list for easy insert or remove of any data. Now, like the array and linked list, there are different data structures which serve different needs. For example, the stack data structure. Here we can see the representation of the stack data structure. We use it to reverse order of items with the LIFO, last in first out approach. Here we can see last in first out approach. A real world example would be undo feature in a text editor or MS Word file. Where the last change we made is undone first. We can see. So here every new action is pushed onto the stack and undo pops the most recent one. And then there's queue, the queue data structure. We use it to maintain the order of processing with the FIFO, fast in, fast out approach. Here we can see in the ticket counter, the checker who fast checks the counter get out with the ticket first. A real world example would be task scheduling in a printer, where print jobs are handled in the exact order they are received. Means the printer prints first things which comes to the pipeline first, then the second, and so on. Here every new job is enqueued at the end of the queue, and the printer dequeues and processes the job at the front first. And then there's tree data structure. We use it to represent hierarchical relationships or stored data using branching structure. A real world example would be a computer's file system where folders contain subfolders and files in a tree-like format. Here you can see in a tree-like format, like we saw here. You see branching level 0, level 1, 2, 3, 4. So here each node can have multiple child nodes, allowing for efficient organization, searching, and traversal of nested data. And then there's hash map, the hash map data structure. We use it to store and retrieve data quickly using key value pairs with near constant time access. A real world example would be a dictionary app where we enter a word, the key, and instantly get its meaning, the value. Here the data is hashed to generate a unique index, allowing fast lookups without searching through the entire collection. And then there's graph data structure. We use it to model complex relationships and connections between items using nodes or vertices, and links or edges. A real world example would be a GPS navigation system like Google Maps, where cities or locations are nodes and roads are the connections between them. So here graphs allow us to efficiently find roads, detect shortest paths, and explore networks in the system. And there's a lot more data structure like these. We will share a list about it. So there's a lot more where each structure makes a specific operation faster or easier. So now we can understand the need of different data structures for organizing and storing data to have efficient access and modification. So it was about the data structures and the need for it. Now let's talk about algorithms. So what are algorithms? Algorithms are step-by-step procedures that use specific techniques to solve problems and achieve well-defined goals. Let's now justify this with a real-world problem. The problem is called find shortest path from source to destination in a grid-based city. Or we can say it like this: find the shortest path in a grid from a source cell to a destination cell. Here we can see we do have two versions of Python codes to solve the problem. This one is the inefficient version on the left side, and this one is the efficient version on the right side. Let's take an overview of the inefficient version. The program begins by prompting the user to input starting and destination coordinates within a 2D grid, where 0 represents a free cell and 1 represents an obstacle. It then initializes a visited matrix of the same size as the grid to keep track of cells already explored during a given path. The core function shortest path brute force is called with the grid, starting point, destination, and the visited matrix. This function uses recursive backtracking to explore all four directions, up, down, left, right, from the current cell, avoiding out of bound moves, obstacles, and previously visited cells. If it reaches the destination, it returns 0. Otherwise, it calculates the minimum of all possible paths from the neighboring cells and adds 1 to account the current step. After all recursive calls complete, the program prints the shortest path length found or a message saying no path found if the destination is unreachable. Now let's run the code and see the output. For this, we will use an online editor called Programmiz. We will select Python editor, then we will run the code. Let's copy the inefficient version and paste it in here. Now let's run the code. Nice, we can see the prompt. It's asking to input the starting coordinates. Here in the grid, this will be our starting and this will be our destination. So for the start row will be 0 and the column will also be 0. Now let's input the destination coordinates. The row will be 2, 0, 1, 2, 2, and the column is 0, 1. Nice, here we can see it returned the shortest path length, which is 3. 1, 2, 3. So this is the shortest path. So we can see how this version of the code or approach works. Now this approach is inefficient because it explores many redundant paths and does not guarantee the shortest path is found early. So this was the overview of the inefficient version, where we have used techniques, recursion, then backtracking, and there's brute force algorithm which uses these techniques, recursion and backtracking, to solve the problem step by step procedurally and achieve the defined goal by finding the shortest path. Now here we can see the representation of the code execution for the inefficient version, where the program begins by calling the function shortest path brute force with the grid, the starting coordinates 0, 0 and the destination 2, 1. A visited matrix is also initialized to keep track of the cells that have already been explored, preventing cycles and redundant paths. Now this function uses recursive backtracking to explore all 4 possible directions, up, down, left and right, from each cell. Let's walk through a key step in the recursion to understand how it works. Suppose the current cell is 2, 0. We have reached it by moving down twice from the start, 1, 2. Our destination remains 2, 1. From here, the function explores each of the 4 directions recursively, 1, 2, 3, 4. Where with direction 1, coordinates 3, 0, which is the down from 2, 0. This cell is out of bounds. Our grid is only 3 by 3. If we see from here, we can see 1, 1, 2, 3, 1, 2, 3, 3 by 3, which means the highest index is 2 for row and column. 0, 1, 2, 0, 1, 2. So 3 is invalid here. So this cell is out of bounds. Our grid is only 3 by 3, indices 0 to 2. So accessing row 3 is invalid here, according to the code we saw. And according to the code, if we see, if this happens, which means the coordinates, row coordinates, becomes equal to the length of row, which is 3. If this happens, then the function returns infinity, according to the code. So according to the code, this returns infinity, indicating an impossible path. After calculating, we get 1 plus minimum of infinity is equal to infinity. Then with direction 2, coordinates 1, 0, which is the up from 2, 0, this cell has already been visited. Here we can see visited 1, 0. So this cell has already been visited earlier in the recursion path. So again, the function returns infinity. From the code, if we see here, if the cell becomes 1, which is obstacle or match any visited cell from earlier, this returns infinity. So the cell has already been visited earlier in the recursion path. So again, the function returns infinity. 1 plus minimum of infinity is equal to infinity. And then with direction 3, coordinates 2, 1, which is the right from 2, 0, this is our destination. So the function returns 0. According to the code here, we can see if the coordinates or cell matches the destination, then it returns 0. So this is our destination, and that's why the function returns 0, representing the endpoint with no further steps. So 1 plus minimum of 0 is equal to 1. And this becomes the best path so far. Here you can see infinity, infinity, 1. So this becomes the best path so far. And then with direction 4, coordinates 2 minus 1, which is the left from 2, 0. Once again, this cell is out of bounds, as column -1 does not exist in the grid. So 1 plus minimum of infinity, according to the code, if we see, if any coordinate become less than 0, then it returns infinity. So according to the code, it returns infinity. So this cell is out of bounds, as column -1 does not exist in the grid. So 1 plus minimum of infinity is equal to infinity. Now after evaluating all directions from 2, 0, the minimum valid path length is 1. So after evaluating all 4 directions from 2, 0, the minimum valid path length is 1. Adding 1 to account for the current step, we return 2 to the previous recursive call. And here for the visited array, to keep the visual representation clean, we haven't displayed all the visited cells in the explanation. Here you can see in this visited cell, all the visited coordinates will be added here. So to keep the visual representation clean, we haven't displayed all the visited cells in the explanation. In reality, the visited array tracks each cell explored during the recursion, marking and unmarking as the function backtracks. Now let's continue with the function's backtracking. As the function continues backtracking, each parent cell, each parent cell performs similar calculation, exploring valid directions, avoiding obstacles and bounds, and calculating the minimum steps required. This process continues until we reach back to the original function called 0, 0. Finally, after exploring all valid paths, and accounting for each recursive step, the function finds that the shortest path from 0, 0 to 2, 1, you can see 2, 1. So the function finds that the shortest path from 0, 0 to 2, 1 is 3 steps. You can see minimum from this 4 will be 2, then 2 plus 1 is equal to 3. So the function finds that the shortest path from 0, 0 to 2, 1 is 3 steps. So this brute force approach is clear and conceptually simple, but it's inefficient for large grids due to exponential recursion. Still, it gives us a great way to visualize the pathfinding process step by step. Now, let's take an overview of the efficient version. The program begins by prompting the user to input starting and destination coordinates with a 2D grid, where 0 represents a free cell and 1 represents an obstacle. Then inside of the core function, shortest path BFS, it sets up a queue to handle the level by level exploration, which is the core idea of the breadth first search BFS. A visited set is also initialized to keep track of explored cells and avoid rechecking them. Starting from the initial cell, the algorithm explores all 4 directions, up, down, left, right, and keeps adding valid and unvisited neighbors to the queue. If the destination is reached, the current distance is returned as the shortest path length. If not, the search continues until either the destination is found or all options are exhausted. After finishing the traversal, the program prints the shortest path length or no path found if there's no valid route. Now let's run the code and see the output. We'll run the code with program is again. Let's copy the code and paste it in here for the efficient version, and Python editor is selected. Now we'll run the code. Run. Nice. Here you can see it's asking the starting coordinate, and our starting coordinate will be 0. From here we will start and here we will end. So starting coordinate will be 0, 0, and the destination coordinate will be 1, 2, 3, 3 and 0, 1. No, 0, 1, 2, 2 and 0, 1 means 2, 1. So 0, 0 starting coordinate, destination coordinate will be 2, 1. Let's input here 0, then 0 starting coordinate. Now enter destination coordinate. Coordinates will be 2. First one will be 2, then second one will be 1, 2, 1. Nice. Here we can see the shortest path length using BFS. We have found 3, like as before. So we can see how this version of the code or approach works. This approach is efficient and optimal as it guarantees the shortest path is found with minimal computation. So this was the overview of the efficient version, where we have used techniques queue and graph-based traversal. And there's breadth first search algorithm which uses these techniques queue and graph-based traversal to solve the problem step by step procedurally and achieve the defined goal by finding the shortest path efficiently. Now here we can see the representation of the code execution for the efficient version, where we begin with a function call to shortest path BFS. We know we are passing in a 3x3 grid where 0 represents open paths and 1 represents obstacles. And then the start position is 0, 0 and the destination is 2, 1. And we also initialize a visited set to track where we have already been. It starts with just the starting point 0, 0. Now at step 1, we start at the cell 0, 0 with a destination of 0. Now we look in all 4 directions, up, down, left and right. Out of these, only 0, 1 is valid. It's inside the grid, not visited and not an obstacle. So we add 0, 1 to the queue with a distance of 1. Then at step 2, next up is the cell 0, 1, which we just added to the queue. The distance is now 1. From here, we again check in all directions. The only valid and unvisited neighbor is 1, 1. So we add 1, 1 to the queue, with a distance of 2. Then at step 3, now we are at 1, 1 with a distance of 2. From here, 2 valid moves are found. 1, 2 and 2, 1. Both are open paths and haven't been visited yet. We add them to the queue, 1, 2 and then 2, 1 to the queue with an updated distance of 3 for both, 3. And then at the step 4, we now check the next cell in the queue, 1, 2 at distance 3. From here, the only valid direction is down to 2, 2. So we enqueue 2, 2 with a distance of 4. Then at the step 5, now we move to the next node in the queue, which is 2, 1. We move to the next node in the queue, which is 2, 1, and this one is special. It matches our destination. Since we have reached the goal, we return the current distance 3. Which we got at the step 3. The distance 3. And that's it. The shortest path from 0, 0 to 2, 1 is just 3 steps. 1, 2, 3 is just 3 steps using breadth first search. So BFS ensures that the first time we reach the destination, it's through the shortest possible route. That's the power of this algorithm for finding the shortest path in the grid-based city. Now let's visualize and compare two different approaches to finding the shortest path in a grid-based city. Here we can see the side-by-side comparison, where on the left we have the inefficient brute force approach, and on the right the efficient BFS approach. Let's break them down. In the brute force method, the algorithm explores all possible paths, even if they are clearly not optimal. As we can see in the diagram, it backtracks multiple times and covers redundant or longer paths just to eventually find the destination. This consumes unnecessary time and memory, especially as the grid size increases. On the other hand, the BFS or breadth first search algorithm explores paths in layers. It systematically visits only the shortest viable options and reaches the destination without unnecessary backtracking like this. So this makes it optimal for the grids where all steps cost the same. Think of how apps like Google Maps work. They don't test every possible street. They use efficient algorithms like BFS to quickly get us from point A to point B. So this was the situation or the case where the BFS, breadth first search, was efficient. Now let's explore a scenario where brute force approach actually outshines BFS. Let's imagine a classic word search puzzle like the ones found in books or mobile apps, where we are given a small grid of letters and the task is to find all possible valid words by connecting adjacent letters horizontally, vertically, or diagonally. The goal here is different. Unlike finding a shortest path, our goal is to explore every possible path, identify all valid word combinations. So instead of stopping early like BFS would, we want a method that doesn't miss anything. For BFS approach, it begins at the first letter, finds one word WORD, stops immediately after the first match. This approach is fast but incomplete. Now for the brute force approach, it starts at every letter, explores every direction from each starting point, finds all possible words like word WORD, row ROW, do DOW, would WOOD, odd ODD. So this brute force approach finds all possible words and doesn't miss anything, unlike the BFS approach where it stops immediately after the first match. So this approach, the brute force, is slower, but it explores everything and finds all possible solutions, which is the defined goal here. So in problems like word search puzzles, where the objective is to discover all combinations, brute force is actually the better approach, while BFS is perfect for optimal shortest path finding. So now we can understand the need of different algorithms for implementing step-by-step procedures with techniques to solve different problems and achieve well-defined goals. So it was about the algorithms and the need for them. So now we understand the need of data structures and algorithms. Now let's reference to the resources. Here's the list of fundamental problems. You can see where each problem includes an ID number, the problem title, and a source link. These problems have been carefully selected based on their relevance, difficulty level, and conceptual value, and are mainly chosen from three key resources. The first one is LeetCode 75 study plan. This is a free study roadmap created by LeetCode, the leading online platform for learning programming and DSA. It includes 75 handpicked problems organized and categorized by topic. You can see the topics: 2 pointers, string, math, string, array, greedy. So these are highly recommended for building a strong foundation in data structures and algorithms. And then the second one is Free Code Camp Coding Interview Prep. This is a free practice course that offers a wide range of beginners friendly data structures and algorithms. Here we can see for algorithms we do have 10 number of different algorithms. For the section data structures we do have 46 of different data structures. So we do have a wide range of beginner friendly DSA and algorithmic problems, which are generally easier than LeetCode ones and are great for grasping core concepts and improving programming fundamentals. And the third last one is additional handpicked LeetCode challenges. We have also included a few extra thoughtfully selected problems from LeetCode to round out and enrich the set. After carefully analysis and curation, this final list consists a total of 97 problems. And then to provide the solutions of these 97 problems, here we can see we do have a code repository in GitHub called Data Structures Algorithms, where we have provided all the code solutions according to their respective IDs. Here you can see, which we have provided here to each specific problems inside of the problem list. Here you can see we have provided unique IDs to each specific problems from 1 to 97. So this repository contains carefully selected solutions to all the problems written in mainly JavaScript. We can check this later in time of practice. These solutions will cover a broad range of data structures and algorithmic techniques designed to enhance problem solving skills and coding proficiency. Here's the list of algorithms, techniques, and data structures, which we are going to cover by practicing problems from the provided list. Now, here we can see a list where we have categorized our problems by the data structures, algorithms, and techniques provided here in this list. And we can see we have provided the IDs to each specific problem here also. So from here we can very easily start our coding practice by selecting a specific topic. Let's say we want to start practicing all the problems related to binary tree data structure. So for that we will first select the problem. Let's say this first problem, the ID is 1. Then we'll go to the solution code repository. Then from here we'll find the solution for the problem 1. Here we can see this is the solution for the problem 1. The repository might not look sorted at first glance on GitHub, but after cloning it locally, the files will appear in ascending order by ID. Like here we can see we have the solution list sorted 1, 2, 3, 4 like this way. So by this we can easily navigate and sync each solution with its corresponding problem. Now to understand the problem and the data structures, algorithms or techniques used in the problems deeply, and also to wrap it up the learning process, here we can see from here you can see we do have rough notes on code execution to the necessary problems solution. These rough notes consist of the execution flow for the problem's main function or the algorithm or technique which is used to solve the problem, which is very much helpful to understand any problem deeply and also to understand the data structures, algorithms or the techniques. So we can check this during the time of learning and practicing the problems when needed. So we can check this when needed. And we can see we do have another rough note on tree terminologies. This consists of necessary topics and terms relevant to the tree terminology, which is very helpful for understanding the tree data structure and solving the relevant problems. And lastly, for the resources, we do have notes on time and space complexity. This note is provided in an organized way. We can see here. So this note is provided in an organized way. We can check this note to learn about the time and space complexity for the programming problems out there. Start from the beginning of this note, and if there's any need for better understanding or for additional info, we can obviously search for that on the internet. So these were all the resources: the problem list, GitHub code repository for the problem solution, list of data structures, algorithms and techniques which are used to solve the problems, then the problem list based on their category, and then the rough notes on the code execution for understanding the problem, and the data structures, algorithms or techniques used in the problem deeply and also for rapid up the learning process. Then the rough notes on tree terminologies for the tree data structures. Then lastly, the note on time and space complexity to analyze and measure the performance of the problem solution. So we do have all of these resources which we will share in the description box of this video. Now that we have covered our discussion on the data structures and algorithms, and also have covered discussing the necessary resources using which we can start our learnings, it's time to make the conclusion of this video here. So make sure to follow the process, fully understand the concepts, and then practice consistently. So thanks for watching.